Hey everyone, how are we doing? I swear sometimes the lights are so blinding. Blinded by the lights. With that, we're going to get started here. A little chill music. We'll do some chapter 19. Oh my gosh, it's the last chapter. It's the final chapter, and I can't sing still. Never can sing. So the light changes. I'm just watching the light change. No one watches the intro anyway, so we'll get the assignments going here. Okay. Let's see here. Assignment manager. Just be able to do the full homework. Okay. Chapter 19 homework. Works easy. Easy homework. Go. Let's do this. Here we go. Okay, this is chapter 19 homework. Gonna get it completed and show how to do it. Show how to do the work right here. So the first. Why's my hair being weird? The first. Okay. We still got shit. 32. That 201. Chapter 19 homework. Question 1. Okay, so when you're doing these questions, the null hypothesis for this chapter is always going to be X and Y are independent of each other. Very, 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 very important here. So I want us to understand the little stat right here. So the null hypothesis is, when we think through here for the null, H sub O, not that one, H sub O, X and Y are independent. The alternative is H sub A, X and Y are not independent. So this is the best way, in my opinion, to write the null and the alternative. So you simply plug in the X and the Y right here. Remember, it's the chi-squared test of independence. So very easy to state the null alternative. You do have to write these out for the test. Towards the end, when you have to interpret, you might be writing some nulls and alternatives. So we just look for the null and alternative stating that they're independent versus non-dependent. So where someone gets hurt and whether the injury is lethal are independent. That means it doesn't matter where you get injured. You get injured on your pinky or you get injured on your shoulder. It's going to be worse. I don't want to get injured there. You don't want to get injured anywhere. But we're going to look for evidence that they're not independent, meaning they have an association. So the null is that they are independent. The alternative is that they're not independent. Now, this is where jump's going to be a huge help. We're going to show some of how to do the work right here, but you want to get a new jump sheet open with File, New Data Table. It's going to bounce around on you, but go to File, New Data Table, Control-N or Command-N will quick key, hotkey it right there for you. You can actually do it inside of anything if you're inside of Word, and inside of Word, you just go and hit Control-N or Command-N. You get a new Word instance, Excel or anything. So Control or Command-N just means Control New, and you can just open up new instances of whatever you want. It's really an awesome quick key right there. One of my favorites. And so now we're going to go grab this data right here. To grab the data, we're going to go to the data button and we're going to click copy on this little button right here, copy to clipboard, and then we're going to hit Control C or Command C, Control C on a PC, Command C on a Mac. We're going to hit done and go back into Jump, and we need to do the following. Make sure you go to edit, paste with column names. I'll pause right here. If you don't paste with column names, you're going to have a bad time and it's not going to paste properly. So you have to paste with column names. Notice how the column is up here, and we can even call this site of injury. It doesn't matter if you do that, but we're going to call that site. Might help a little bit with the way we describe this. So we have the site of the injury and whether it's fatal versus not fatal, and this is the table. Next, we're going to go to tables and go to stack. I'll pause right there. Tables, stack. Now you're going to double click both the blue columns with the quantitative values, and you get the preview of what it looks like. Double click both blue columns, only blue columns. Now click OK. Once you've clicked OK right here, you can see the site and the label. You can change the label to the outcome. Doesn't matter if you change the names of these. To change the name, you just double click and rename it. It just helps a little bit with understand what we're analyzing. The site of the injury and the outcome of the injury and the frequency or the count. And this is count data, which is the fourth condition when testing two categorical variables. Condition 1, random. Condition 2, less than 10% of the population sampled. Condition 3, after we pause, is going to be expected cell counts are greater than 5. More on that in a moment. And also condition 4, the fourth condition is count data, meaning both variables, site and outcome, are categorical, leading to count data. So now we are going to go to analyze fit y by x. Analyze fit y by x. You're going to put if the site might explain the outcome. Notice how site explains why there is an outcome, and the data has to go into the frequency. This is the counts of the observation being a count data. Does site explain why there is a certain outcome? We're going to put the frequency of observations there. Let's click OK. We get the following output. You can see body had more fatal and head neck had more fatal. Limb had less fatal. The non-fatal in limb, less than 50% of limb injuries were fatal. We're also going to click this red arrow right here. You're going to deselect everything but count for right now. This is the counts of observations we had previously, and now we're going to deselect counts even more, and we're going to go here and put in the expected counts. So these are literally the expected counts, and we'll show how to get one here in a moment. But the expected counts are what go right here. Make sure it goes in the same order. Body, head, neck, limb, fatal, not fatal. So I'm going to have to move this to the other screen, but we're literally just going to copy in these numbers. It says the 2 decimal places. I think you can actually change this in JMP. I think there's a way if you right-click it, you go to Format, and we go to Fixed Decimal with 2 decimals. There we go. Look at that. So that was right-click, Format, and then Fixed Decimal to 2 decimal places. And now it's formatted for us. We just put the values in there. We're going to show how to get it in one moment, though. So stay tuned. I'm going to show how to calculate this by hand, which does appear on the test. So there's that value. Really? I tried to tab over, and it said no. It said, I am not tabbing over today. It's very easy to make an error while doing these, so be very careful. It's just punching in the right number. You do get multiple attempts. I wish it told you which ones you got wrong. Or do one of these by hand. There we go. We should get it right. There it is. Now, let's show how to do it by hand right here. This is the by hand calculation using the counts. So if you were doing this by hand, you'd have to do the following. The mathematics to get the Excel count, expected count. The mathematics to get the expected count is the following formula. Row total times column total over grand total. Row totals times column total over grand total equals expected cell count. And what you do here is you simply circle the row total, and then you circle the column total. Then you circle the grand total in a color that's going to appear better. And you simply write the equation. Row total times column total over grand total equals expected. And that's the expected just for this one cell. So let's solve the mathematics. You have to do it for all the cells. It can take a while to do by hand. It doesn't hurt to do these by hand. But 120 times 65, we're just timesing the numbers, just literally doing this equation with those. And then you divide by 148, and it's 52.70. If you look, that's what we got there in the top corner. Or we can also view it here by adding it back in. We can go to expected. 52.70, and that's the value. So it's row total times column total over grand total is the expected cell count. The chi-squared test statistic is found down here at the bottom. It's the Pearson chi-squared test statistic, which is the sum of all the cell chi-squareds. We're just showing how to get this. But if you were to get all the cell chi-squareds, well, I guess I got to show how to get it. A singular cell chi-squared, like 27 right here, would be found the following way. To find 27, the mathematics you have to do, we're going to show how to get that 27, is going to be observed minus expected squared, quantity squared, over expected equals a cell chi-squared. And so the observed is going to be what you saw, the 20 you saw. The expected is how many we get when we expect by random chance via the row total times column total over grand total. And we take their difference in squared and divide by the expected. So literally, we're going to plug in, I'll write the number so you can see it. 20 observed minus 6.62, square that quantity over 6.62, and that equals the cell chi-squared. So here we go. It's going to be 20 minus 6.62. Sure, we got close enough. 20 minus 6.62, square that quantity, and then divide by 6.62. And there it is, 27 point, and it might have carried some more decimals in the background, but 27.0 something, 27.04, 27.03, because JUMP's probably carrying extra decimals we don't see. And so that is the cell chi-squared right there. And what you do then is you take all the cell chi-squareds and sum them up to get the Pearson chi-squared test statistic. So this value down here at the bottom of the screen, the 44, is the sum of all these values. If you literally take all the cell chi-squareds, which are a standardized metric of distance of how far the observed and the expected are away. If you notice, this one's really small because 59 and 53 are kind of close, where this one's really big because 20 and 6.62 are further away. It takes into account how big the expected is because you're doing observed minus expected, squaring it to make it positive, dividing by the expected to standardize it. Because it's like, I mean, if something went up from $53 to $59, that'd be a pretty price increase. But if something you buy went up from, let's say, or something you buy went up from $6.62 to $20, that'd be a bigger jump. It is a bigger amount, but it'd be like, wait, that was $6 last week and now it's $20? Or if something went up from being like $2 to $9, that'd be a bigger jump too. So you have to look at what the expected is when you're standardizing things. So we standardize by the expected. Okay, so the sum of those values is the 44.124. And we just put it in right here. And you can do these all by hand, but it's not fun. And how many degrees of freedom? The degrees of freedom trick is the following. Notice how there's 3 here. This is the degrees of freedom trick, and it is on the screen, but here's the trick. This is a 3 by 2. 3 by 2. So you hold up your fingers and you say 3 by 2, and then you drop one finger on each hand. 2 times 1. 2 degrees of freedom. It also works the same if you delete one row, delete one column, and in doing so, you're left with the 2 degrees of freedom right in there. And so it is rows minus, I'll write the formula. Degrees of freedom for the chi-square is equals to rows minus 1 times columns minus 1. Rows minus 1 times columns minus 1, 3 by 2. So you go 3 by 2, 2 times 1. And so there's 2 degrees of freedom. There we go. I didn't see the p-value, but it should be close to 0. I'm going to guess 0. Yeah. You know why? I'll tell you why. The differences we see here, just even thinking about it, are not possible by random chances. Like, wow, all those people lived who got hit in the limb. Maybe they just got lucky. No. These differences are so large, they're virtually impossible. And there's the p-value right there, basically 0. If you do a little swirly trick and hover over this, you can see the p-value. There we go. It's 0.000000000262. I think I got it about right. Very, very small. Virtually impossible by random chance to see these differences if there is nothing going on. So we think there is a relationship that where you get hit is associated with whether whatever happens. I 100% reject the null. Since the p-value is low, I reject the null. And this means we do have evidence, so we do conclude that they are not independent. They're related in some way. There we go. That was a really good question. So we basically did a little mini lecture. That's, if you understood everything right there, you understand this chapter. That's the majority of this chapter in one question. So let's do another. Another one. Where's it? Is he not on here?
Wow.
Let's do it. Start 201. Chapter 19 homework. Question 2. Okay, so this one right here, same idea going on. Whenever you write a null and alternative for the chi-squared test of independence, you do it the following way. You always put the null is that 2 things are independent, and the alternative is that they're not independent. Remember, this is the chi-squared test of independence. One of the easiest ones to write the null alternative for. So the null is that the site of the injury and the weapon you get injured with are independent. The alternative is that they're not independent. We're not doing the homogeneity test. That's a different test. Notice that this is a 3 by 3. If you want to figure out the degrees of freedom right now from the previous question, you can do it pretty quickly. Let's go put the data into JUMP right here. Follow these steps. Click on the table. Click the button here. Copy to clipboard. And then hit Command-C or Control-C to copy it. Next, go over to Jump, and inside of Jump, go to File, New, Data Table. File, New, Data Table. Now, make sure to hit Edit, Paste with column names. Optionally, we're going to click the column one right here, double click it, and we're going to call it Weapon, and click Enter. Twice. So now we have this. We're going to go to Tables and Stack. Tables, Stack. Double click only the blue columns. Then click OK. Double click the blue columns, you should see this, then click OK. Now we have our data ready to analyze. Notice it says label, we're going to call it site. I double clicked it, just making it nice and pretty. Site, we got the weapon and the site of injury. And I think we're doing, does site of injury explain weapon used? Does site of injury explain weapon used? Sure, let's try it that way. Okay, we got our data ready to go. And let's do analyze fit y by x. Does the weapon explain where someone gets hit? We'll find out if I did it reverse. And then make sure to put in the data. I'll pause here. If you don't put in the data, you're going to have a bad time. I've forgotten to do it before. Does the weapon explain where someone got hit? Sure. Click OK. And we see arrow, rock, ground, all that. Ooh, we did it. It does say limb down there. That's an error. That's an error. That should say sword. That's an error they've had for a while. Ma Pearson, what are you doing? That is an error. It's been there a while in this question. We're going to delete down all of these and get the expecteds. Now, remember, we can solve an expected by hand. Know how to get an expected by hand. You need to do row total times column total over grand total. We wrote it out previously, but watch as we do this right here. We're going to do one expected by hand. To remember the formula for it, we're going to do the amount of people we expect to get hit with an arrow in the body. So you circle the row total, you circle the column total, you multiply them, and you divide by the grand total. So we would expect, by random chance, the amount of people to get hit with an arrow in the body to be the following. We'd expect 5.05 people. And we can get the same thing right here with Jump really quickly by clicking just expected count, and it'll do all the math for us. And we can right-click here and go to Format. And under Format, we're going to go to Fixed Decimal and go to 2 decimals. And now we get it formatted. We'll bring this over here and type in the numbers. Okay, does it say 2? It does say 2. Why round when you don't have to? You can't tab. Why tab when you can't tab? Once you know how to do these, they're very, very repetitive, which is good. Just do a bunch. Get them down. This violates the expected cell count condition. A lot of these cell counts are way less than 5 expected cell counts. The expected cell count condition states you must have at least 5 successes, or expected successes. It's kind of like the at least 10, but you need at least 5 successes expected. So, and the chi-squared test statistic is the sum of all the cell chi-squareds. I wish it had us find a singular cell chi-squared. If you want to find a cell chi-squared, it is observed minus expected squared over expected. So if you went and found all the observed and expecteds, that top one's pretty easy. This one right here, it's going to be about 1.8. And let's see how I knew that. And 1.82. Let's see what it is. So the answer to that one is, I say it's about 1.82. The answer is, we'll see how I knew that. Cell chi-squared. 1.85. Darn it. Close. How did I know? I said it was 1.8 something. I should have just said 1.8 and then it would have still rounded. It's because you do the following. You do observed minus expected. Observed is the top one. This is the observed. This is the expected. And then you quantity square it over expected. So what I noticed is it's 2 minus 5.06, which is basically 3 or 3.06 squared. So you get, it's basically 9 over, and then it's going to be over 5. So that's where I said, oh, it's about 1.8. And then I noticed that you have this little change on the end of it right there, making it bigger. So that's where I made my guess at. If you think about, go to a bigger one. Sure, this one. That one has a difference of about 6 because that's what you're measuring is the distance. So it's going to be 36 over about 50, but it's a little smaller. It's going to be 35 over 50 because it's not quite 6 squared. So 35 over 50, it's going to be about 0.7, 0.7, a little smaller, 0.698. Oh, 0.68 right there. Close enough. So you should know how to get these. And then what we do with all of these is you have to get the sum of the cell chi-squareds. You have to figure out how much total deviation there is. And all you do is you literally add the cell chi-squareds to get the chi-squared test statistic. If you sum those up, you get the chi-squared test. And that's the value you see down here with the Pearson, which is 12.104. There we go. That should do it. There you go. And the degrees of freedom, you say, Brian, this is a 3 by 3. So 3 by 3 has 2 times 2 degrees of freedom. What do I mean by, Brian, this is a 3 by 3? It's literally 3 answers here and 3 answers there. If you delete one row and delete one column, you get the total of 4 degrees of freedom. There are 4 cells left in here. And that's got it. That's the 4 degrees of freedom. And that's the answer right there, 4 degrees of freedom. And what is the p-value? The p-value would have to be found by plotting it on the chi-squared distribution. MuBot will show us a chi-squared right here coming up in just a second. Let's find out. Come on, MuBot, chi-squared. So we have to go and say with 4 degrees of freedom. What else can you say, done? We want to find the p-value. So with 4 degrees of freedom and a chi-squared of 12.10, the p-value to 3 decimals is this. This is a very unusual result, very unlikely by random chance. And there it is. So using an alpha of 0.05, our p-value is below alpha, so we reject the null. This is evidence to conclude that they are not independent. We have evidence that they are related in some way. That's got it. Well, that was easy. I know it's easy when you know how to do it, but no big tricks. Nothing crazy. My email is acting super weird, and I don't like that. I don't like that one bit. We'll find out. All right. 23, 13, stand to 1. I can't believe it's the last week of school. Here we go. Suppose we include a test of independence ends up rejecting the null, so we have evidence that they are not independent. Which of the following conclusion is appropriate? I think this is so tricky the way they phrase this. I don't like this question. Multiple choice, multiple guess. We don't say that they are dependent, really. That almost sounds like one variable must depend on the other. They have an association in some way. If it just stopped at they're not independent, I'd be fine with that. It's not that one variable depends on another. There's some sort of association. I don't like it. It's like it almost feels like either of these could be correct. I don't love that question. I don't love it. Okay, just fill in. For all chi-squared procedures, the sample size assumption is checked by the expected cell count because that says we need at least 5 expected successes and at least just 5 expected. I'll show you how to check it here in a second. It's the expected cell count for you can see. The way you check it is you literally look at your expecteds and you see if they're all bigger than 5. One way to do this is to just look at the cell with the smallest row total and the smallest column total. So if you go to 9 and 29, you see how it doesn't matter that it's 5 in there. Rock knows.
It doesn't matter.
You would go to that one right there, and I'll explain. Because remember, we're trying to figure out how many we would expect. It's not how many we observe, which is the count. So if you go to the smallest row total and the smallest column total, you'll get the smallest denominator on top of the equation. You're dividing by the same amount of time, so as Rock knows,
it doesn't matter.
So you can check this, and for this cell right there, we would expect, let's figure it out, 9 times 29 divided by 140. That's not at least 5, so we fail. We'd expect 1.86 successes, observations in that cell. And you can double check your work just by looking here at the expecteds. And 1.86 right there, and that is the smallest one because the smallest column total and smallest row total. So the expected cell count is how we check it. And The degrees of freedom for a chi-squared test of independence are based on the dimension of the data you're working with. Remember, we said this is a 3 by 3. You just drop one finger. 2 times 2, it's 4. The formula is row total times column totals over grand total. This is more like a t-test. T-test is n-1, or the complicated 2-sample t. Level of significance is alpha, has nothing to do with degrees of freedom. So the dimensions are what does it. It's rows -1 times columns -1. Okay, last question. I'm going to go eat some lunch. We got the whole homework in this video. Help people out, get the homework done. People are like, man, you're so quick today. I said I was a busy day. Null hypothesis. X is independent of Y. Alternative hypothesis. X is not independent of Y. So, it's that easy. If you know where to look, you know where to look. They really want us to jump right into the chi-squared test. So, traditionally, you would be finding your expected counts. Then you do observed minus expected squared to get the cell chi-squareds. You add up the cell chi-squareds to get the Pearson. And they're just, hey, Brando, we're going to hop off in a moment here. I had a late start and I've got lunch over there. Woo! We're almost done. I've got this full thing marked. Check it out. Mubot saying hey in the chat. We're going to copy the data right here. Copy to clipboard. Copy, Control-C or Command-C. Go into Jump and go to File. Check out those points. I'll throw you some points here in a moment. File, New, Data Table. And then you know what we're going to do. A little edit, paste with column names. Brando getting some more points right there. Brando, great job on those points. We got to make some new levels. Another 5,000 points. We're going to change the top of this column right here to age group. Age group. Oh my gosh. There we go. And we got the age group located right there. And now we're going to go in and go to the following. We are going to go to Tables, Stack. Tables, Stack. We're going to double click the blue columns and then click OK. OK. And then we're going to change this to outcome of the pregnancy. And then you don't have to. I just like double clicking and making it look all pretty right there. And then we go to Analyze, Fit Y by X. And we say, does the age group explain why it is a certain outcome? Does age group explain why it's a certain outcome? And do not forget to put the data down there in the frequency, the count observations. Does age group explain why it's a certain outcome? Let's click OK. Looks like no. Looks like about the same late term and early term, and the p-value is very high. And there's the chi-squared of 3.09. It probably rounds to that. 3.09. It'll round. It'll round. Round, round, get around. I get around. It worked. So find the p-value. What was it? Can I remember it? Oh. Once again, if we want to find it ourselves, we have to look at the graphic and say, this graphic right here, the table is a 4 by 2. 4 by 2, which means 3 degrees of freedom. 4 by 2, 3 by 1. So 3 degrees of freedom. Because 4 reduced by 1, 2 reduced by 1, 3 times 1, 3 degrees of freedom. You have to put in the chi-squared 3.09. And there we go. And the p-value is 3.78. What did I say it was? No way. I was really one decimal off. You can also just look at the jump output. There it is on the bottom of the jump right there. It's the Pearson with the p-value, and there it is right there. So it's very close. This p-value is way greater than the alpha level. So since the p-value is high, you just let the null fly. You do not have evidence of association that someone's age group is associated with when they give birth. So the p-value is way greater than alpha. There is insufficient evidence for the alternative. We do not believe that someone's age group is related to whether they have an early or late-term pregnancy. That is the full homework. We did it pretty quickly, but that's everything. We'll probably do more, especially tomorrow. We'll do more of the quiz. But that's the full homework. That's it. Good work. Until then, I'll let everyone go. I don't know, my email's acting all weird, but I'm going to go eat some lunch and relax for a moment. We got class, got big stuff going on. End of the semester. Bye for now, everyone. Bye, Brando. Bye.